In Chapter 2, we're going to learn how to transcribe DNA into RNA, which is actually not quite very difficult to do. So we're going to make it more interesting by adding a few extra requirements like mutating strings, reading and writing files, and such. So to get started, let's look at the Rosalind page for this. Given an RNA string that looks like this, we are going to turn all the T's into U's. And that is not a difficult problem to do. As I show here in the introduction to the chapter, given a string, there is a method on strings. There's a function that I can call called replace, and I can say replace T's with U's, and it will give me exactly what they asked for here. Given this string, they want this sample output. So since we already we can do that in just one step, and a lot of the basic ideas of what we're doing in this chapter are similar to what we did in the first chapter, I have decided to add a few more requirements. The first one is that we're going to write a program that's going to accept the inputs as one or more files, which is a very, very common task that you'll be dealing with in bioinformatics. And we're going to write the output into directories, so we're going to need to know how to see if those directories exist and how to create them. Then we're going to need to learn how to open and write files. We haven't done that yet. And also the various ways that we can modify strings. So we've already seen replace, but there are some other very interesting ways I'd like to introduce you to. So to get started, we're going to go into the 02 RNA directory. Now before we do that, I'm using UV, so from the base directory, if we do an ls-la, we'll see that there is a v directory, and if you don't have this, then you probably need to go to the beginning of chapter 1 and see how to do the setup with the tool called UV, and that looks like UV like this. And so the first thing I need to do is to instantiate my virtual environment with UV, which I do with which I can actually do with source.venv bin activate. And I have a couple of windows here that I'm going to be using to write and test my code. So I'm going to activate them in both. And just to be sure that I'm using my virtual environment, I can say which Python 3, and I find that it is finding the one that is in my biofx directory. And so I know I'm good there. So with that, the first thing I'd like you to do is to copy the first solution into a program named RNA. And as you saw from the first chapter, we need to call the solution a particular, sorry, I need to be in the O2 directory there. I need to call the solution a particular file name so that the tests will work. And so let's give an idea of how the program should work, what I would like it to do. And when I say should, what I mean is that it will conform to the tests that I've provided for you. You can always write the tests, you can always write your programs however you like, but I am trying to teach you some good habits here. So starting with this chapter, I'm going to be really challenging you to go off and try to write the solution on your own, given the things that I've already showed you and some hints that I'll give you along the way. And then I'm going to show you various solutions. For this chapter, I have two solutions, one using string replace and the other one using re.sub. I'll talk about that. So what I would like to see is when I run your program with -h, I would like to see a usage that looks like this. And it's a good time to spend a little bit of time here on some of the shorthand that we see here. So these arguments that are shown in square brackets, the square brackets are a common convention in Unix command line programs to show that the arguments are optional. So that's why it shows up under here, options, the -o dir and --out dir. You see here in this shorthand that they are shown in square brackets. File is not shown in square brackets, so it is a required positional argument, but it is additionally followed by more file objects, file arguments, and they are in square brackets, so this next one is optional, and the ... means that I can provide as many as I like. So one or more positional arguments, which I see here are supposed to be input DNA files, and then optionally I can specify where I'm writing the output, and I see here I've already been given a default value of out. So makes it really easy for the user to run. And again, that user is probably going to be you. So make your life easier by providing reasonable defaults for optional arguments, and by creating a nice interface that is documenting so that you don't have to go read your code in order to figure out how to use it again. So that is what I would like the program to create for the help. And let's look at how it's going to work. So under tests inputs, there, let's just look at tree real quick. Under tests, there are 3 inputs, which is very similar to the first one. And there's also a RNA test.py, which is exactly what we saw in the first chapter. And if you look at the test code for that, a lot of it's going to look identical to what we looked at in that first chapter. And so I can cat this file and see that it is the input string from the Rosalind page. And what I would like to see is that when I run the program, using that as the input, it has now created, if I look at tree, it has now created an out directory that didn't exist before, and there is an input1.txt. It is the same name as the input1.txt here. And if I cat out input1.txt, I see that it is the same sequence, but all the t's have been replaced with u. And if I want to run this, specifying an output directory of RNA, and I want to run it with all of the input files here, and I'm using what's called a glob here on the command line to specify to bash will turn this star into all the files that are in the test inputs directory. If I run it like this, it now says that it wrote 5 sequences in 3 files to the directory RNA. And that's a really useful output. It tells me exactly what it did and where I can go to look to find the output. And if I look at tree now, I see there is indeed an RNA directory. There are 3 files there. I can additionally use the WC program, which is for word count, but I'm specifying -L to only count the lines. So I can specify, I can ask how many lines are in each one of the output files. I see that there's 1 in input 1, 2 in input 2, and 2 in input 3. And if I look at that, if I compare that to test inputs star, I see it's the same. It has the same number of lines. So each line in each input file has been put into an output file. And if I cat all of the RNA star directory files, cat is going to concatenate them. It's going to turn that into one giant output, and I see indeed there are no t's in here, there are only u's. And if I were to do that on the tests inputs directory, it would look like this. So all of that seems to be working well. If that is enough for you to go on, I challenge you to stop the video here and go write the program and use the tests to guide you. If I say pytest-xv, I should pass all of the tests that I have provided, and that is all I ask for you to do. Write a program that will pass the tests that I've given you. So if you feel brave, go do that. If you would like a little more direction, just stick with me and I will walk you through this. So to get started, I would like you to use new py. I am going to use it with the -- force flag to overwrite the existing RNA. So let's look at this real quick. If I say I want new py and I want to call it rna.py, then you will see it says that it already exists, and do you want me to override it? Now I have an option here of yes and no, and very common to write this such that these are my options, this is what I should respond, and if I don't respond with anything, if I just hit enter, then N is capitalized here, showing me that it will be the default value that is chosen. If I say no, it will not overwrite and we'll say goodbye. And if I run it instead, new py with --force, then it will overwrite that. I also want to add the program description of transcribing DNA to RNA, and I want to call it DNA. I want to call it RNA.py. So if I do that, and then I open up RNA, I see I have a nicely formed program here that I can start with, and I can whittle it down to have the arguments that I need for this specific program, and I think that that is an easier way to start than trying to write all this from scratch. So given that, I want to modify the getArgs function to have an output directory first. So I can change any one of the ones here, but it just needs to be a string, a type of a string, and I have an example of having a named argument that has a string. So let me go down here, and the first thing I'm going to do is I'm just going to change S to O, and I'm going to change outdir to outdir. A note here about the style, you could actually use a dash here, and argparse will turn that into an underscore as far as the variable name, the slot where you can get that. So it's up to you whether you want to use underscores or dashes there. And I want to call the help for this, it's going to be the output directory. And the metavar, it's more than a string, it's a dir. Directory. So that is a good indication for the user to understand that that's what we're providing here. The default type is always string, so I'm really not gaining anything by typing string here, but it's not bad. I can leave it. And I do want to set a default value. So since this is an option, I'm going to set the default value to out. And that is all I need to do to set up the out directory. Remembering again, the short flag is given first here with -o. A single dash and a single character is the common way to do a short flag. And then the long flag starts with 2 dashes. And the long flag is going to be the name of the slot that where we can retrieve the value from argparse. So that's really kind of the important one that we create here. So given that, I want to now create a positional argument. So there's a couple things I can do here. I usually just go up here and modify this positional. So it is a positional argument, not because I've called it positional, but because I've called it a name that does not start with a dash. So I'm going to change this to file, and the help is going to be input DNA file, one or more. I'm going to and the metavar here is going to be file. And what else here? In args is going to be important. So this will be the number of arguments. And it doesn't matter what order I put these arguments in. So if I do it differently from the book, that's okay. In args is going to be plus, and I'm going to explain that in just a moment. That indicates that I want one or more values. And this last one here is well, let me put this in first, and then we'll talk about it. So the type of this argument is going to be this argparse.FileType, and I'm additionally giving it the arguments R and T. R means I want to be able to read this file, which is the default, and T is that I want this to be a text file. It's going to be opened as a text file. It doesn't actually enforce that the input is text and not a binary file, for instance, but this is really controlling how the file will be opened, and we're going to be talking about opening files for writing in this chapter as well. So that is the default. If I wanted, I could just use with no arguments whatsoever. Now, when I wrote this book, and I was writing this in 2021, and published in 2022. This was the recommended way of accepting and validating file arguments with argparse. It has been deprecated. I find that sad. I really like this, and so to be fair, the authors don't want you to use FileType anymore. But since the book is using it, I'm going to go ahead and show it to you. And I could talk about how to get around it. Essentially, you'd have to open the file by yourself. But I'm going to show you why this is so cool, and then I can explain to you what you'd have to do to get around it, to code all this for yourself. So those are the only two. If we go back and look at how we want this program to work, there's only two things I need to define here: the out directory and the input files. -H is handled for me, and all of this will be handled. This is handled by the number of args, and this is handled by the fact that this is an optional argument. So that means I don't need the rest of these arguments. I'm going to get rid of them. And that's going to parse my arguments into this args, and it's only going to have file and outdir. And so let's talk for a second about what that's going to create as far as the structure of our arguments to the program. Oh, well, let's go over this real quick. In args, I have a little table here. It describes the number of arguments. You can use this, you will be using this to define lots of different ways of accepting arguments. You can specify a number, which will be exactly how many arguments you expect, like 1 or 2. Or you can use a question mark for 0 or 1, the star for 0 or more, and then the plus is 1 or more. And between that and the exact number of arguments, I always find that I can define exactly how many arguments I want for something. And then we talk about here using the file type to validate the file arguments. One of the great things here is that just by defining with file type, if I give it a file argument that doesn't exist, for instance, blarg, if I try to run it, it's going to blow up in the get_args function. It's going to say I can't open that file, when it's going to give me a really clear error string that says that there's no such file or directory blarg. And all of that is handled for me inside of the get_args function. And the program never even makes it out, because it will detect that it's not a valid file. It prints a usage statement, an error message, and it exits with a non-zero value, which is a key part of what we're trying to do here to indicate that our programs fail to the operating system. And that's important, because then pipelines that we write that incorporate our code will know to fail at a particular step, so that we can correct the errors. For instance, there's a truncated input file that needs to be fixed. So this is important. And the cool part is that we don't have to write any of that code. So let's talk about how we're going to define the arguments class. What are the types that describe a list of open file handles and a string? So the first one is I like to call, as much as possible, I like to call these slots in argparse the same thing as I put into my args structure. And so here this can be called outdir. Just make sure, yes, So those are the only two things I need. Outdir is a string, but file is going to be a list of text IO. Now text IO is something that I've already brought in here. It's something that, because I'm showing you by default how to create a argparse argument, and so I need to bring in list. So list, name, tuple, and text IO are three types that I'm bringing in from the typing module, and this is going to describe a list of open file handles, and that is the key, that when I define with file type, this is no longer going to be a string. This is going to it's going to open the file inside this get_args, and what it's going to return are file handles that can be read directly, which is another really nice thing about this. I'm going to call this files. Because it is a list, it is a plural. It is I generally call the argument itself in the single, and because it could be a single, but here it will always be a list. So Args file is going to be a list, and so even if there's only one element, it's going to be a list with one element. And then outdir is going to be Args outdir, and that's going to be all for my arguments. So a lot of times the way I get started is I will just print args. At this point, I would like to run my program and see that it's working okay. So I've called it, sorry, I need to be in my O2 RNA. I've called it RNA.py. There is a directory called RNA here. I want to get rid of that for a moment so that I can just run RNA. If I run it, I'm seeing a pretty good help message. Let me run it with -h. That looks great. Let's run it with an input file, tests input, input1.txt. And what I see is something that looks kind of cryptic, but it is my Args structure here, my Args class. And inside of it, it has files. And we see that files here starts with a square bracket, which means it is a list. And then we're seeing this something, a text.io wrapper, telling us that this is an open file handle. I can see that the name of the file is the file that I gave it, and it shows me how I opened it. I opened it in R, read mode. I can see the encoding as this is UTF-8, and I can see my second argument here, my second slot here in my name tuple args is called outdir, and it has a value of out. So that's really good stuff. I can definitely move ahead with writing my program. A note here about how I could return these arguments. It's not necessary for me to have the names of the arguments of the slots as long as I'm giving them in the same order that they are defined in. So files comes first and outdir comes second. So I could put args.files and args.outdir. It is safer and easier to read if you have the slots. You can also, if I were to happen to change the order up here in my args for some reason, I get busy and I happen to move things around, then this version of the code would break now because I'd be trying to put in outdir into the first slot, or files into the first slot, which is now outdir, and that would be bad. So I have written new PY to always put in the slot names so that it's just safer that way. I recommend you do that. So let's outline our program using pseudocode. So if you've stuck with me this far because you want some more help, let's talk about writing pseudocode. So the idea here is you sometimes, again, it can be hard to start from the blank page. So sometimes what you need to do is just write out the steps that you know that you need to do, and then you can figure out how to do them one at a time, and which is what I've done here. The first thing that you're going to have to do is to determine if the output directory exists, and if it doesn't, you need to make it. And for that, I've given you a couple lines of code here. I used this code just countless times in a week. Going back to the OS path module that we saw in the first chapter, and we looked at a function called isFile there, and now we're going to use the one called isdir. And so we're saying if it's true that this is not a directory, so the isdir returns false. If it returns false, then it's not. If the outdir directory does not exist, then we want to use os makeDirs to create it. And so I can just take that and pop it into, get rid of my print, and pop it in here. And that right there is all I need to do to create the output directory. So I've handled that for you. And one of the things that I always do is I like to print when I get to the bottom of my program so that I know when I'm done. And so I'm just going to start off by printing done so that I know I get here. And let's just, it's always good to just add 1 or 2 lines of code and then go from there. So given that, I can see right away that I've got a problem. It says name OS is not defined. Did you forget to import OS? I certainly did. So I'm going to jump up here. I'm going to import OS, and then I'm going to run my program again. And I get to the part called done. And if I look here, I see that there's an out directory. Actually, it's probably left over from before, but that's okay. So there is an out directory. I see there's nothing in it, and that's fine. So that part worked. Now, when we saw the output, the actual final thing that was printed to the screen from our program, I showed you that I wanted to know the name of the output directory. So I see done, but I want to know the name of the output directory, and I want to know how many sequences and how many files were created. And so for that, we're counting things, again, just like in chapter 1. So I need a couple of variables to keep up with how many things I've counted. And what I suggest is that you, oops, skipped a little ahead there, is that you create two variables, one for the number of files and one for the number of sequences. And I showed this way of initializing more than one value. I could do these on two separate lines. So let me do this. I will say that there's a lot to be said for putting them on separate lines. So this is arguably the more Pythonic way to do this. And so maybe for the purposes of this video, I'm going to put them on two separate lines. The nice thing about this is if I wanted to initialize one, or I wanted to get rid of one of them, like I'm no longer going to track the number of sequences, I could just delete the line, and now I'm left with the other one. So this is the probably more Pythonic way to write this. This is a shorthand way of essentially creating a tuple on the right side and then unpacking it into a tuple on the left side. But I'm actually breaking the tuple down into separate variables over here on the left-hand side. So however you want to go about that, two different ways, they both accomplish the same thing. So I'm going to copy this pseudocode. Well, I'm just actually going to copy the first thing. I'm going to iterate over the files, and I'm going to use a for loop for that, and I'm going to call the value that I'm using here FH, because these are file handles, and FH is something I've been using for decades to indicate to me that the variable is a file handle. I have a note here real quick. I forgot to mention this. OS makeDirs will create a directory and any parent directories that are needed. So if I were to run this, for instance, let me comment this out. Let me go over here. Let me run my program again. I'm going to rm-rf, my out directory. I'm going to run RNA. I'm going to say I want to put this into foobar baz. It was going to be the output, and I'm going to say test inputs input 1. And if we look at this and we look at the tree now, you see foobar baz has been created, 3 structures here, 3 nested directories. And the nice thing is OS makeDirs created all of the parent directories along the way. Let me just show you real quick. If I get rid of that, rm-rf, the foo directory, and if I were to run this again, but instead I used the function makedir, this will fail because it's trying to create the subdirectories and the parent directories don't exist yet. So I always just use makeDirs because I'm not sure what I'm going to get from the user. And I don't want to go to the trouble of making all those parent directories, so I always use makeDirs. I never use this makedir. Recommend how you do that. Let us stop for a minute, and before we go over the iteration, let's just see how we're doing on PyTest. So let me just go back and make sure that this is working. Yes, if I run PyTest -xv, the X is to tell it to stop on the first failing test, and V is verbose. And I see actually I'm already passing a lot of tests. I'm passing the fact that I created the program called rna.py. It prints a usage. It dies when I give it no arguments. So for instance, if I just say RNA, I get a helpful error message that says, nope, I need at least one file argument. If I run this with a bad argument like blarg, I get this really handy error message. And if I echo the exit value of the previous call, I can see that is a non-zero exit value. Let me, I haven't introduced that variable, but I'm using ZSH here on my Mac, very much like bash, and there's a special variable in the shell called $? which is the exit value of the previous process. And if I were to just say echo hello, that's going to echo hello, and it's going to be fine. It's going to exit with a 0 exit value. So what I can see here is that when I ran RNA with blarg, that it threw up. It did not like that argument. There is no such file, and it exited with a non-zero exit value. So I got all of that for free just by creating a nice interface using argparse. I've not done really much for the program. The program doesn't do what it's supposed to do yet, but there's a lot of basic stuff that's been handled for me. So with that, let's talk about how to iterate over the input files. So like I said, I'm going to create a for loop, and I'm going to go over args.files, and I already talked about this in the first chapter, but I have a little bit more about this. If you want to use for I is an okay, it's a barely acceptable variable name in the very limited context of, say, going over a range of integers. X might be okay for X and X's. That would be kind of a very functional programming mathematical way of writing something in a very generic way. Maybe X's is just some iterable of something that you don't know. X might be an okay variable name to just indicate you really don't know what the thing is. But when you do know what it is, you should really give it a variable name that describes it. And FH is, for me, always and forever will be a file handle. So I'm going to iterate over the file handles. And let's just, it's always good to just start by printing things. Printing is a great way of figuring out what your code does. So with that, let's run RNA with tests, inputs, all of the inputs. And you see here it does something. Maybe you don't understand what it's printing, but it is certainly printing each one of those files, the file arguments, and it's doing something. So now let's look at our pseudocode again. What we need to do is open the output file in the output directory. And this is actually pretty good structure. I'm just going to copy this and I'm going to paste it. And the structure here is pretty good too. So I'm going to indent these two lines. So we want to open an output file in the output directory. For each line or sequence from the input file, we want to write that transcribed sequence into the output file. Then we want to update the number of sequences that we've seen. And when we're done processing the file, we want to update the number of files that we've processed. And at that point, we will be able to print an output statement here at the bottom that tells us what we did. So moving ahead, a few pointers about how to create the output file names. So what we want is we already have the out directory. We know that right here, args outdir. And we've gone ahead and we've made sure that the output directory exists. So now we need to create a file name for the output file. And we've already imported OS, but what I'm showing here is if I go into my REPL and I import OS, and I have a file like tests inputs input.txt, there is a function in the OS path module called dirname that will tell me the directory part of this. And I have a little graphic here. This dir name returns this part of a file path, and then the thing that returns the other part is called base name, so the right side. So if I change this from dir name to base name, then I get that, and those are directly equivalent on the command line to dir name of this and base name of this. So if you are coming from shell scripting and you're used to doing this kind of thing in a shell script, you can do exactly the same thing inside of Python, and they have conveniently used the exact same names, dir name and base name, to give you those substrings. So using that, I can extract the base name and substitute the given input directory name for the output directory name, and that will be the path that I want. And to create that path, I'm going to use the function called ospath.join, because I want to make sure that my program will run both on Windows and on Unix. And these two different operating systems use different path dividers. So on Unix, we use slash. The thing pointing to the right is called a slash. You don't need to say /, it is a slash. The thing that points the other way to the left is called a backslash. So there's slash and there's backslash. So I can create my output directory, my output file name, by concatenating, joining the output directory given to me in Args and the base name of the input file. And for instance, that would create RNA input txt1. So let's write that. I'm going to just copy this out of my book, but I do recommend that you type it out because it will help build muscle memory. But for this, I'm going to keep this moving along here, and I'm going to ospath.join the out directory with the base name of fh. So fh is this, what we saw here when we were running this, fh is this object that has different slots in it. It is a text IO wrapper, but it has this name slot in it that I can call. That's what I'm calling here, fh name, and it's going to give me this. And so I can say, ask what is the base name of that, join it to the output directory, and then just to give me something to go on, I want to say, I want to print this file name is going to be moved into, or the output of this is going to go into this output file. And it's always that's a good stopping point. Let's run this. And that looks great. And if we do a tree, I see that there is, let's get rid of that rm-rf on foo, and let's go back to tree. We see that there is an output directory, and let's run our program again, and I see that test inputs 1 is going to be put into out input 1.txt. Great. That is such a common task in bioinformatics that is really worth knowing how to do well. So moving ahead, let's talk about how to open the output files. So we're going to be now using the open function. It's built right into Python. And we didn't have to use that on the input files because by using a file type argument, argparse tried to open them for us. And when it was unable to open them, for instance, the file doesn't read, that we can't read a non-existent file, then it just bailed. But we are going to use open here to open it in open the output file in a mode for writing, and so it will create the file. If there's a reason why we can't create the file, like for instance we don't have permissions to write to the output directory, we will see that as an error message as well. So there are a couple things that we need to know for the writing mode, and we saw that. Let's just jump back up here. I said when this was created, it had RT in here, and I said that is the default value. So R is for reading. You can also have W for write and A for appending, which means that if the file already exists, it will just open up and start adding more content at the end of the file, which is as opposed to W for write, the file will be overwritten entirely as soon as it is opened. So RT is the normal way to open a file. We don't actually have to specify that. So what we want to do is, and the other is how we want to be writing the content, whether we want to be writing it as text that will be interpreted. Usually that will be like a UTF-8 encoding, or we can read and write raw bytes, which you would want to do. For instance, you're reading the pixels out of an image that you're using for some sort of machine learning. Normally, you're going to probably be reading and writing text mode, and text is the default, so you don't have to specify that. So given an output file, I'm going to create, so output file to me is like a file name, like a path. Output out FH is, FH tells me this is a file handle, and out FH tells me this is where the output is going to go. So I just know in my head this means that this is a writable file. So I'm going to add that line now, and it's writable because I've passed this argument of WT. The W means write, and the T is optional. The default is to write text, but it's not a bad idea to put that in there. So now I have, let's just run this. Let's just make sure that that works. And we can talk for a second about, I'm going to chmod my output directory. Let's see, first I'm going to chmod it to 000 out. And what that is going to do is it's going to make it so that the output directory has no permissions. So if you've never learned how to read this column in the long output from ls, this is the first character is what type of a file it is. So a dash is the default, it's just a regular file, but this starts with a D, so it lets me know this is a directory. And then there is an octal notation here, 3 octal groups to let me know read, write, execute. So you can see read, write, execute, read and execute are the bits that are on for RNA, and read and execute are the bits that are on for, so this is for the owner, for the group, and for everyone else. I believe I have a whole discussion about this in Tiny Python projects if you want to dig deeper, but I have removed all the permissions from the output directory. And so if I were to try to run this now, I would get, my program will blow up because I now am trying to open a file in a directory that has no permissions. So that is what you will see here if you have a problem like this in your program. And what I would say about this is that I would not attempt to put in a lot of special error handling in Python code. I would just let this program fail. So this is creating really just a fatal error that the program itself cannot correct. We really have to go back to the user and say you need to specify a different output directory, or you need to fix the output directory. So to me, it's perfectly acceptable for this program to simply throw an exception and fail right here. So let's figure out how to write the output sequences now. So we've got this a level of for each file handle in Args file. We've got the output files, we've opened them. So now we're down to for each line or sequence from the input file. So for, and how do I call it here? For DNA in FH. So file handle, if we go back and remind ourselves what we're looking at, let's cat tests input1.txt. Each, let's do one that has 2 lines. Each line of this is a string of DNA that we want to turn into RNA. I could call this for line in file handle. Technically it's a line, but that's not the most specific variable name that I could use. It is a string of DNA. At least it's supposed to be. And I'm assuming and I'm treating it that way. So I'm going to call it for DNA in FH. Now, I don't need to do anything special with FH. It is a file handle. It has been opened, and I can treat it as an iterable. And in this context, it's going to give me each one of the lines in it. So it's just a very handy way of interacting with the file system. And what I want to do is to create. Let's just start off by printing. How about that? let's start off by print DNA, and let's talk about what we're going to see here. Let's run our program rna.py with that, rm-rf, the output directory. Let's sudo that, and you know what? Let's now let's try that again. What we're going to see here, and let's remind ourselves what the input looks like. Why is there an extra new line? So we would expect that it would print this line and print this line, but it's printed this line and then it printed another new line and printed that line and another new line. And the reason is because when we're iterating over each one of these lines from the file handle, the new line is still attached to it. So we have a couple of options here of not printing that. One of them is to use the rstrip function on the string. DNA is a string, so I can call rstrip on it. And if I run this again, then I will see that's what I expect. Let's go ahead and get rid of that. We don't need to see that anymore. So that is what I would expect to see. So I can either rstrip that, or the other option, and I'm going to comment that out for a second, is I can tell there is an option to print called end. And I can say at the end of the line, just print nothing. And that also works. So we talked a little bit about some of the options to print in the first chapter, and I talked about, for instance, the separator that you could use, and I also introduced end. So here is two different ways of not printing a new line, an extra new line. So with that, instead of printing DNA, we want to print DNA where we've replaced the T's with U's. So let's do that. And if we run this, we now have a program that's essentially doing what we want to do. The point of the Rosalind was to simply replace T's with U's, but we're trying to make it more interesting by putting this now into the file that we just wrote, that we just opened. So the question is, how do you do that? I have a little sidebar here to talk about the fact that the DNA string itself is immutable. So what has happened here, this is important, and I'd like to point what's going on here. Let's create a DNA string that has ACGT. And if I say, let's take this bit here, what do we have? We have actually a new string that's been created for us that this returns. This does not modify DNA in place. This is something that we talked about with tuples, and why I think it's important to use tuples to represent the arguments, and that is because the tuple itself cannot be modified. I can't change an individual value inside the tuple. Similarly, if T is in DNA, let's just ask that. This is a way of looking at set membership. So it's saying, is there the letter T in the string DNA? And that's true. And I can actually use something called like the index function to find where T is in DNA. And if I look at DNA at position 3, that is indeed a T. So if I were to try to do something like, say, change that to a U, that would not work. DNA is a string, and strings are immutable inside of Python. The only thing I can do is create a new string. And to do that, one way to do that is to replace the T with a U, this string replace that we've been using. I'm going to show you another way to do that as well, but it's going to always be creating a new string. So that's actually, to me, kind of fascinating about Python. Tuples and strings are immutable. You cannot change something inside of the value. You have to create a new tuple or a new string. If you were to say help print inside the REPL, it will give you really nice documentation that shows you the end argument here that we're using. We talked about sep, And the other one that's going to be important for us is file. So this is where we want to write the output, and you see it defaults to something called sys.stdout. We pronounce that standard out. So sys is the system module for interacting with the operating system, and on the Unix operating command line, there are two output channels. One is called sys.standardout, and then there's another one called standard error, stderr, and we will be using both of those. It's very important when we have errors that we print them to standard error so that they don't get mixed up with standard out, and we can find the errors in our programs. So we want to use the file argument to print the output. So I'm going to say file is equal to out.fh. And now instead of printing the output to the standard out, it's going to print it into the output file handle. So let's run this now, and we see we no longer see the T being replaced with U. And if we were to cat out, there's an input2.txt, and we see that it has two sequences, and the T's have been replaced with U's. So we're pretty close to completing our program. Let's see. It does not like the output of the program. So even though it is creating the right output, the test is not happy with what our program says at the end, because our program is currently saying done, and it says it does not equal that it has this longer string that it wants to see. Done wrote one sequence in one file to directory out, so we need to correct that. So in order to write that, we're going to need to update our variables. I do have here that another option is to use the out.fh write method. So let me show you how to do that. Instead of replace, I'm still going to write this, and I'm going to, I believe that's all I'm going to need to do, because one difference between print and write is that write does not add a new line at the end. It writes exactly the bits that you tell it and nothing else. Print by default adds a new line without being asked, and so if I say out.fh, now this is a method that I'm calling on the object out.fh. Out.fh write, and I'm telling it what to write, and I don't need to tell it file out.fh because I'm saying out.fh, and I don't need to tell it not to print anything at the end because it doesn't, by default, it will not print anything at the end. If I rm-rf my out directory, I guess it doesn't exist. Let me run this again with tests inputs star, and if I cat out star, I see it has indeed written all of the files that I want. Actually, let me do head on output star. And what's nice about head is that it puts these separators in, so I can see that out1 has this single sequence, out2 has the two sequences, out3 has the two longer sequences. So two different ways of writing the output into the output file, one using print, one using out.fh write. Now we need to work on the final bit here, which is how we want to print the output. So I already have here in my pseudocode that I need to, so write the transcribed into that, transcribed sequence into the output file, and then update the number of sequences processed. So to do that, I say number of seqs plus equal 1, and then here update the number of files, num files plus equal 1. And now I can use this to tell me to create something like this. There is, if you would like to pause this and make that happen and then get a full passing suite, full passing test suite, and come back, I will show you how to finish up this statement, finish up this program. So if you are still with me, I'm looking here at some of the tests and how I structure the tests. You see here there is something that's testing for a bad file. The tests are run in order, and so I generally try to put the tests that break my program before the tests that test for good output. So for instance, testing with a bad file, one that doesn't exist, I expect that to fail just right away. And that's a key part of writing programs, especially in bioinformatics. You want your program to fail as quickly as possible if it's given bad input. You don't want to spend an hour or two processing some input file only to realize at the end that you can't write the output file. That would be pretty terrible. So it's better to figure out right away to figure out those problems as quickly as possible and to fail right at the beginning of the program. So I have, this is what the test for a bad file looks like. I have a function that creates a random file name that makes sure that doesn't exist on the system, and it tries to run this with that randomly bad generated file name, and it asserts that the return value is not equal to 0, and that I'm using here, one of the reasons I'm showing you this is that I've brought in the RE module for regex, and I'm going to introduce regexes here a little bit more. But I'm looking for a pattern that looks like usage in the output. And I can also additionally say, I want to ignore the case. So if you were writing your own version, basically, of argparse, or using some other tool, and you wanted to capitalize usage, what this would do is it would match any upper or lower case. It doesn't matter. It's just going to ignore the case, and it's looking for the word usage followed by colon. And by doing match, I'm saying I want this match to start at the beginning of the string. So the output from the running the program starts with something that looks like usage without regard to case. And then search is another function that the RE module provides. It looks for this string anywhere in this output. So it's looking for no such file or directory, and then the name of this bad file that I created. And the reason why this test is written like this is because it is important to me that your error message should give me as much information as possible. So when you say no such file or directory, what file or directory? And it's this bad input that I've created by creating a random file name. So I expect that the output from dying on a bad file should include what the bad file name is. So that is something to know about this test bad file function that I wrote. So for instance, this is what it would look like on this randomly generated file name. You see here, this is actually, I had to break this line for the book because it's a very long line, but this is actually a single line of output if we were to run this on the command line. And you see it's a very long line, and so I'm looking for this part of the error message, which is not at the beginning of the line. It's just kind of buried somewhere in all of this output, and that's what the regular expression search does, is that it tries to find this string anywhere in all of this output. Regular expressions are really, really cool. Here is the test I wrote for input, and it may seem a little tedious that I'm going over these tests, but there's a lot of just systems programming kind of stuff here that you can learn by reading this code. For instance, it's going to be extremely common as you're writing Python programs in bioinformatics that you're going to need to go out to the operating system and run some other program with some arguments, and then you're going to need to see if the output that you expected to be created exists. And that's exactly what all of this is doing. So here's a really handy function I'm using. I'm bringing in the shell util module, which is what I need to remove a directory structure, which is something that you will need to do sometimes. So I'm saying if the output directory exists, I want to remove that output directory so that I can then run my program. And this is defaulting to the out dir, right? So if it's using that default out directory of out, I want to get rid of it, and then I want to run my program with this input, assert that it ran correctly, assert that the output looks like that I want, assert that the directory was created, and then assert that the output file that I expected to be created in the output directory with this name by using ospath.join, that it is a file that exists. And when I open that file and read it and then strip off the last new line, I assert that the value inside of that is this string. This is all the kind of stuff that you will need to do all the time in bioinformatics. So it's good to have this as example code that you can use. This is one instance when I'm using exception handling. Exceptions will basically just make your program blow up. If you want to catch exceptions, you use something called a try block. So blocks in Python start with a colon here at the end of the line, and then the lines that belong in the block are indented after that. So all of these lines belong to the try block, and I'm actually not doing anything with the exception. I'm not. There's usually a try catch is what you'll see, and you try to catch. You can catch specific exceptions, and I will just say most of the time, most people do a very poor job of handling exceptions, and it's very easy to think that you have handled them correctly, and you haven't, and then therefore your program will fail in wildly unexpected ways. So unless you really care to learn how to handle exceptions correctly, just don't. Let your program fall over. Let your program fail, and then use that information to fix whatever is the problem and run it again. And in this way, I have it somewhere, I think, in the book, but that's what's called the happy path. We're really just programming here the happy path where we expect the program to run to completion without problems. I'm using try here so that I have a finally block, because what's happening is I want to make sure that the output directory is removed at the end of this. So no matter what happens in this try, if any of this fails, like for instance there's a bug in my program and it doesn't run, I don't want the output directory to still be hanging out. So I'm using a finally block to catch the exception, ignore it because I'm not doing anything with in the catch block, and then to run, finally just run this bit of code regardless of what happens up here. So with that, there's some stuff here about Pylint that may or may not be so important anymore because I'm really not using Pylint these days in favor of some other ways. So let's go over the two solutions that I have for you. The first one uses str.replace, so you've already seen that. So here is the entire solution that I've come up with using that. Well, we import what we need from the OS and the typing modules. I create a class arguments that has a list of text.io arguments for the files and a string for the output directory. We have get args here that handles all of the tricky stuff for making sure that I have one or more file arguments passed as positional arguments, and then an optional output directory that defaults to out, and then I pass those to args for the file and the out dir. And then here we have creating the output directory. We're iterating over these, creating the output file handle. I've showed you, this is the option I showed you how to use outfhwrite to replace the T's with the U's. And then specifically here, you could also call outfhclose. So it is also very typical. Another way that you might see this written in Python would be to use a with open as outfh. Is another very, very common way that you would see this. That becomes its own block. And one of the ideas here is that when outfh passes out of scope, when we've left this block, outfh will be closed automatically. I'm not a huge fan of the width. It's fine. I have come from a background of being more declarative like this, and so I typically say out fh open. Call open like this and assign it directly to a variable. The last part here that's a little bit tricky is I now have the number of sequences and the number of files, and I need to create the output. So let me just introduce something real quick. If I'm going to put num_seq is equal to, say, 1, I need to choose whether or not to put an s at the end, and when it's 1 sequence, I don't want an s, and when it's 0 sequences or 2 sequences, then I want an s. So the case is that I want nothing if num_seq is equal to 1, else I want an s. And so when I set num_seq equal to 4, for instance, this will produce an s. And so we've already seen an if statement. So if some condition, if true, print hello, and that will print hello. But what I'm now doing is I'm saying print hello if true, else ugh. I'm using an if expression. So the thing that happens for a true value is placed first, then I say if true, else, and then the thing that I want for the false value comes at the end. And that's what I'm writing here. So when you see here, print an f string, wrote num_seq, and then I'm going to say sequence, and then there's this bit here in the placeholder where this is a bit of code that's being executed. What it's saying is that I want the empty string if number of sequences is equal to 1, else I want an s. And then I do the exact same thing for files. And so it's a little bit to type, so I'm just going to take this line, and instead of that print, I'm going to have this print. And I need to indent these, and I can format my code real quick. And now when I run this RNA, and I'll use tests, inputs, all of the inputs, it tells me it wrote 5 sequences and 3 files to directory out. And if I instead use input 1, it says it wrote 1 sequence and 1 file to directory out. And it's not obviously important that your programs have good English grammar in their statements and their output, summaries, but it is useful for you to know about the difference between an if expression, which is what this is, and an if statement, which you've seen before, like in chapter 1. So with that, we now have a program that should entirely pass our test suite. It does. And with that, I would like to show you a second way to write this because it introduces the idea of regular expressions. If you're not familiar with them, they've been around since, I think, the 1950s. And there's a really good O'Reilly book called Mastering Regular Expressions that will teach you all about them. They are a separate language that came out of mathematics that are used to find patterns in regular languages. And if you want to know what regular languages are, that's a whole other branch of linguistics. And it doesn't matter. What's important for us is that we can import RE. So let's do that. I always like playing around in the REPL. So I'm going to import RE, and I can do help on RE to find all kind of things about regular expressions. And they use a lot of special characters. So you can just look. We've already seen where I was using RE search, like for instance RE search for this character in yes. So I am sorry, I've copied too much here. I just want this line. Let me clear my screen. If I give it just a regular character, most regular characters just mean what they mean. But what we started to see here in help RE is that there are a lot of special characters that mean other things. So the dot doesn't mean a dot. It means any character at all except a new line. The caret, or this little hat, does not mean a hat. It means the start of the string. And the $sign means the end of the string. And when you want these as literal values, you have to put a backslash in front of them to escape them, or you can put them into square brackets to create a character class. So you are still able to match a literal dot, but if you put a dot in your regular expression pattern, then it actually means any character except a new line. So with that, the reason why that's important is because, for instance, if I say I want to search for this pattern, what it does is it returns a match object, and it tells me that the match that I'm looking for is from 3 to 4. And if we were to say, let's put this into ACGT. I'm going to put it into a variable, and I'm going to say re search in DNA for T. And it tells me it goes from 3 to 4. And if I say DNA from 3 to 4, which is the way of subscripting a list or an iterable, it goes from 3, and it doesn't actually go to 4. It goes to 1 less than 4, which is 3. So it pulls out 3, which is essentially the same thing as just doing this. We already saw this. I showed you that I could not, for instance, I showed you this in the context of trying to overwrite that as a U. That's not possible. But what's cool about this is that I was using index to find this. And let me show you, if I were to say DNA index of T, it's also going to tell me 3. But if I were to say DNA index of X, it actually creates an exception, which makes my code blow up, which is not what I want at all. I just simply want to say, if there's a T, then replace it. I don't want to be calling a function that could introduce an exception, and then I have to get into exception handling, and that's a whole business, and I'm not going to go down that road. So I don't actually use index. What happens if I try to use a regular expression to search for X? Whoops, need to switch X here. What happens is that it doesn't seem to do anything. Let's put that return value RV into that, and I'll say, what is the type of RV? It is the none type. Oh, RV is none, true. So when the search does not find a match, it just returns nothing instead of an exception, which is far, far better. So I never use index. That is a terrible function that will break your code. I use re search, or I could use, the simplest thing was T in DNA. We saw that at the beginning too. It's another way of trying to find if one substring occurs in another. And so using this, why is all this important? Because there is another function inside the RE module called sub. And it's not doing anything that replace doesn't do for us. Because we're just trying to do the exact same thing of replacing one letter with another. But it is able to do far more powerful things like find a pattern of text, like say some sort of restriction enzyme that could be any mix of characters, followed by some other characters. It can find all those variations in this pattern and replace it with some other value. This can in certain instances be a great thing to be using because it's far more powerful than just than string replace. So what I want is re sub, and I want to substitute T for U in DNA, and I get exactly the same string as before. So this is another way to write this program. I would go up here and I would say import RE, and then I would go down here, and instead of DNA replace, I'm just going to comment that out, and I'm going to say RE sub T for U in DNA. And how do I know that that works? Let's see. Did I make a mistake? The tension is palpable. I did not. So this version of the program also works. And I know that because I have a test suite that checks it for me. So two different ways to accomplish the same thing. I'm showing you the exact same thing, but using a print statement. So I need to strip the input DNA, or I need to say end is equal to the empty string. So those two different ways of doing that, and I've now introduced just a little bit the idea that there are these things called regular expressions. I highly recommend that you go off and learn regular expressions because it's a language unto itself, and it's useful on the command line, it's useful in grep, it's useful in Bash, in Python, in Perl, in Rust. Pretty much any general purpose programming language is probably going to support the use of regular expressions to find patterns of text. So I've shown you two different versions. Which one is better? Well, it depends on what you mean by better. Which one is faster? That's a good way. A lot of times we just care about performance in bioinformatics, but one of the things I was trying to stress here is that better here, if we were looking for actual patterns of text, like for instance IUPAC codes, where ambiguity is represented, like we're looking specifically for T. Well, what if we want T or C or T or G? That's represented by IUPAC codes. So we could take all the IUPAC codes that include T, and we could put them into a pattern for regular expression and match any of those characters and replace all of them with U. It's kind of a trivial thing that you probably never would do, but it's a reason why you would want to choose regular expressions over, for instance, iterating over each one of those IUPAC codes and replacing it yourself. Far easier to do re.sub. So how do we determine which one is faster? Well, I have two solutions here in this directory, solution 1 and solution 2, and I could do a for loop for py in solution. So if you don't know, at the command line, you're in a programming environment. You can do a for loop over this glob pattern. So this is going to do solution 1 and solution 2. I can say do. I have to, so I'm in Bash essentially. Technically I'm in ZSH, but it supports the same syntax. Do. This is what I want to do. I want to echo py, and now since I'm on the command line, I have to interpolate this variable by putting a $sign in front of it. Ampersand ampersand is and. So do this, echo py, and time, so execute time by running this Python script on the largest input file, and then I say done to end in the for loop. And so it ran both of them, and it ran it with time so that it told me how long each one took. And I see here that it really doesn't seem to have actually it does. I hadn't tested this. I'm in ZSH, and apparently it doesn't handle this. So if I were in Bash, I would be able to see. Let's just look at this output. When it executed these things, these programs, it looks like one took 1 second, and the other took a lot less than that. And so the re.sub looks like it takes a lot less time. Well, does it? We really have extremely little information to go off of. So there is a program here in this directory called Youens-Clark. And if we look at it, let's look at H. I didn't give it any defaults. I didn't give it any arguments. So by default, it just started creating a sequence of length 1 million and writing 100 of them into an output file. You see that all of the arguments are optional. So if I don't tell it to do, give it anything, it will just go off and create a big file. And so let me just let that run for a second. And while that's running, we'll look at this here in the book, where in Bash here I ran for each one of those solutions, run the program on this very large output file. Let's see if it's done yet. So when I wrote the book at the time, it generated an output file that was about 95 meg, which is a respectable size. It's still on the small side for what we deal with in bioinformatics. But let's look at what seek looks like. So it's actually a pretty big file, and we see it has 100 lines with quite a large number of bytes here. So if I were to say WC -L on this, I see that there's 100 lines. If I say just WC on it, I see that it's quite a big file with a lot in there. So if I were to say, for instance, time solution 1, replace this with seek.txt, and then do the same thing with solution 2. Solution 2, it's not just. There we go. We see here that does seem to take quite a bit longer when I run that with 0.223 and then 1.23. Takes quite a bit longer to run with regular expressions. So that first time that we ran it, it seemed like the regular expression one was quite a bit faster, but then really when we gave it something more like realistic input, we see that the string replace is far faster than regular expressions. And that makes sense because the regular expression engine is doing a lot more work than just string replace. So going further, and the other thing I would say is that this is a really pretty rough way of benchmarking. There are entire benchmarking suites for actually verifying and running multiple iterations over multiple inputs to really see under realistic conditions which program is faster. So this is not the way that I would actually recommend you go about benchmarking, but it just gives you a rough idea of what is happening when you benchmark something. And I would recommend you look at the GenSeek program that I created. You might find that something like that is useful for you in your own testing. So going further, modify your program to print the links of the sequences to the output file rather than the transcribed RNA, and then have a final status report to tell me the maximum, minimum, and average sequence lengths. So there you're not writing this transcription program. You're actually writing something more like seek magic. There are lots of programs that you can use. Easel. I wrote something called Seeker in Rust to give me some statistics on input files. And so, given some sequencing run that you are needing to analyze, maybe the first thing you want to do is just know an average length of the sequences that were found. Maybe there was some problem in the library prep and everything got truncated and you really just have no usable data. Things like that. That's what there are many programs for checking the quality of sequences and just giving you general statistics like that. And so write one of your own. It's not going to be as good as the ones that are out there, but you will learn a lot by writing it. So tell me the maximum, minimum, and average sequence lengths in a file. That would be useful. So some key points. We talked about argparse.FileType, and I mentioned that as of the time of recording this video in 2026, this has actually been deprecated. It's still there, however. I can still use it, and for many reasons I like it. For very simple scripts, I still like to use it. I will tell you that if, for instance, you're trying to open a bunch of output files with this or a lot of input files, you can actually very easily exceed the number of open file handles on your operating system. That has happened to me more than once by using file type as the argument in argparse. And so it's not always right to do that. A lot of times I will just use strings and then attempt to open them myself and print those errors as well. We talked about in Args for argparse to specify one or more, two or more, or one or more, zero or more, or an exact number. We looked at isdir. We had seen isFile before. We used os makeDirs, and I explained the difference between makeDirs and makedir. I always use this one because it creates the parent directories. We used the open function for the first time to open files for writing, and so we talked about the W option that you have to give for that. We talked about that files can also be opened with the B mode if you want to read pure bytes, so just zeros and ones. If you open it with text mode, then those zeros and ones are interpreted as characters. Normally they are in UTF-8 encoding, and that's a whole thing if you don't know what UTF-8 is. I actually have I talk a lot about it in my book Command Line Rust if you're interested to know more about how to read files as bytes. And finally, we talked about the fact that strings are immutable, so there are methods that alter strings into new strings so you never are able to change a string in place. And we specifically talked about str.replace and then the re.sub functions. And that is chapter 2.